Welcome to The Explainer. Today, we're unpacking what is honestly one of the absolute most elegant problem solving blueprints in computer science and operations research: dynamic programming. If you're the kind of focused learner who loves taking a massive, complex computational challenge and just optimizing the heck out of it by never solving the same problem twice, well, you are in the right place. We're looking at a foundational roadmap today that shows exactly where this approach makes its biggest impact. We're not just going to talk theory, we're going to look at the massive scope of real-world problems this mathematical blueprint actually solves. Okay, let's dive into this structured roadmap. We've got three main stops today. First, the core characteristics. Second, management and budgeting. And finally, logistics and reliability. Let's kick things off with Section 1, the core characteristics, building the foundation. So before we can apply this blueprint to anything out there in the real world, we really have to establish what makes a problem solvable with dynamic programming in the first place, right? It's not just some generic strategy for breaking things down. To actually use this approach, a problem has to have two strict mathematical properties. First, optimal substructure. This basically means that the absolute best solution to a massive, complex problem inherently contains the optimal solutions to its smaller subproblems. There's no room for conflicting dependencies here. Solving a little piece locally must contribute directly to the global best answer. And then we have the second property, overlapping subproblems. Honestly, this is where the magic happens. In a naive recursive approach, you might end up solving the exact same subproblem thousands of times, literally wasting immense computational power. But dynamic programming spots these overlaps and essentially says, hey, we've seen this before. Which brings us to the two main ways we actually implement this: memoization and tabulation. With memoization, we go top down. Start with the big problem, break it apart, and every single time we solve a subproblem, we cache that result. So next time that specific subproblem pops up, boom, just pull it straight from memory. Tabulation, on the other hand, is the bottom-up approach. We start with the smallest, most trivial subproblems, solve them, store them in a table, and just iteratively build our way back up to the final massive problem. Both of these methods guarantee one fundamental rule: you never ever do the same work twice. Once you lock in these core tenets, optimal substructure, overlapping subproblems, memoization, and tabulation, an entire universe of applications just completely opens up. Which naturally leads us to the ultimate question. Where do we actually apply this dynamic programming approach? I mean, it's one thing to have a beautifully elegant set of mathematical characteristics, but if it doesn't solve actual tangible problems, what is the point? So let's pivot into a rapid-fire catalog of vastly different real-world use cases that really prove just how wildly adaptable this blueprint is. That brings us right to Section 2, management and budgeting, corporate applications. Now, what's really interesting about this juxtaposition, straight from our source text, is how totally different these two things sound. On one hand, we've got priority management employment smoothing. This is fundamentally an HR and operations headache, right? It's all about optimizing your workforce levels over time so you aren't just wildly hiring and firing people, which we all know is incredibly costly and disruptive. You want to smooth out that employment curve. But then, on the other hand, we have capital budgeting. This is pure corporate finance. It's looking at a limited pool of financial capital and deciding exactly which projects to fund over multiple stages to absolutely maximize your long-term return on investment. On the surface, HR smoothing and financial capital allocation seem like they're speaking completely different languages. But underneath the hood, they are both multi-stage decision problems completely governed by dynamic programming states and stages. In both of these scenarios, you're moving through distinct stages. Think month-by-month staffing needs or sequential funding rounds. The crucial insight here is that decisions you make today actually constrain the resources you have available tomorrow. Hiring 20 people right now changes your starting state for next month. Handing a giant bag of cash to Project A limits the capital left for Project B. By clearly defining the states, which are your current resources, and the stages, which are your time periods, dynamic programming can evaluate every single possible sequence of decisions to find the absolute optimal path. It's literally the exact same structural blueprint, solving two completely different boardroom headaches. How cool is that? Now, let's transition smoothly into our final section, Section 3, logistics and reliability, physical and systems problems. Our source gives us three fascinating areas here, and this brilliantly illustrates the sheer versatility of dynamic programming. First up, the stagecoach, or shortest path problem. Think about physical routing, whether you're pushing data packets through a global network or trying to route delivery trucks through a messy city grid. Dynamic programming calculates the absolute most efficient route using the principle of optimality. Instead of just randomly guessing paths from the start, a super common approach here is to actually work backward.
You start at the destination and figure out the lowest cost to reach it from the immediate preceding nodes. You just keep stepping backward, stage by stage, building up this table of optimal subpaths until, bam, you're back at the starting point. The global optimal route is inherently built from those optimal smaller steps. Okay, second, we've got cargo loading, which you might know in computer science as the classic 0/1 knapsack problem. Imagine you've got a transport vehicle with really strict weight and volume limits, and a massive warehouse full of items with varying values and sizes. At each stage, meaning for each individual item, you have to make a discrete choice. Do I pack this item or not? Dynamic programming systematically evaluates this by weighing the value of the current item against the remaining capacity at each stage. It basically builds a table checking every possible capacity level against every single item, ensuring the final configuration maximizes total value without, breaking the truck's axles. And finally, reliability problems. This is all about keeping incredibly complex multi-component systems from failing. If you have a strictly limited budget to buy backup parts for a critical machine, where exactly do you place those redundancies? In this case, the state is your remaining budget, and the stage is each individual machine component. Dynamic programming calculates the marginal increase in reliability per dollar spent on a redundant part at every single stage. It perfectly allocates the budget to maximize the overall uptime of the entire system. So whether we're talking backward routing, capacity optimization, or marginal reliability gains, the exact same core characteristics are doing all the heavy lifting.
We have covered a massive scope today, pulling directly from our source syllabus. We started with the foundational math of optimal substructure and overlapping subproblems. We jumped straight into the corporate world of employment smoothing and capital budgeting, and then we navigated the gritty physical challenges of shortest path routing, cargo loading, and system reliability. Whether you're dealing with money, people, or physical cargo, it really all boils down to the exact same elegant process, optimizing those overlapping subproblems so you never ever do the same work twice. So I want to leave you with this final provocative thought to take away from this explainer today, knowing that you now have a mathematical blueprint capable of optimizing literally everything from human resources to global logistics. From employment smoothing to cargo loading, which of these dynamic programming problems will you solve first?